Every single time you visit a secure website, your computer and a completely unknown server across the world agree on a locked vault without ever sending the key. It seems physically impossible. The process starts with a simple greeting. Your browser sends a list of cryptographic languages it speaks, proposing the mathematical rules for the upcoming exchange. It is a menu of complex algorithms. The server replies, picking the strongest, mutually supported algorithm. This single choice dictates the mathematical battleground where the rest of the communication will occur, setting the parameters for the key exchange. Now comes the hardest part. They must generate a symmetric key for fast encryption, but any data sent over the wire can be intercepted. How do two strangers securely create a shared number? Modern connections solve this using elliptic curves. The server and client agree on a specific curve and a starting point on that curve. These are public parameters anyone listening can clearly see. Each side generates a massive random number, keeping it strictly private. They then perform a special mathematical operation, multiplying the public starting point by their secret number to create a new public value. This operation is a one-way street. Calculating the new point is incredibly fast, but working backwards from that point to find the original secret number would take modern computers millions of years. The client and server send these calculated public values to each other across the open internet. An attacker sees these points fly by, but without the secret numbers, the data is useless. Here's the magic trick. By multiplying the received public value with their own private number, both sides independently arrive at the exact same coordinate on the curve. This is the shared secret. The attacker only has the two public points. Because they lack either of the private multipliers, they cannot compute the final shared coordinate. The math physically locks them out of the vault. But wait, how do you know the server you just exchanged keys with is actually your bank and not an imposter sitting in a coffee shop intercepting your connection? We need authentication. The server proves its identity by presenting a digital certificate. This document contains the server's public key and is digitally signed by a trusted third party, acting as a cryptographic passport. Your browser uses the trusted authority's public key to verify the signature on the certificate. This mathematical check ensures the server's public key genuinely belongs to the domain name you requested. With the identity verified and the secret established, the raw coordinate is fed into a key derivation function. This algorithm acts like a cryptographic blender, expanding the secret into multiple distinct keys. This expansion ensures that even if one aspect of the handshake was slightly predictable, the resulting symmetric keys possess maximum entropy. They are completely indistinguishable from true random noise to any observer. These derived keys power an authenticated encryption scheme. Not only does this obscure the data being transmitted, but it also mathematically guarantees that no one alters a single bit in transit. To confirm everything, both sides send a final message, encrypted with the new keys containing a summary of the entire handshake. If the summaries match perfectly, the secure tunnel is officially established. Because fresh private numbers were generated just for this session, even if a hacker steals the server's master identity key tomorrow, they cannot decrypt the conversation you were having today. The past remains safe. In mere milliseconds, pure mathematics has built an impenetrable fortress around your data. This intricate dance of algebra, probability, and trust happens behind the scenes for nearly every click you make online.